All right, this is the last lecture on chemical equilibrium, chapter 15 in the Burge book. Again, what is chapter 15 about? It is the toolbox required to do the materials in chapter 16 and 17. So, everything we've talked about in this chapter is about definitions, applications, different ways of manipulating the equation and how that affects the equilibrium expression. And um, so, and then doing ice tables, initial change, equilibrium, plugging that in to find out equilibrium concentrations, reaction quotient. All this stuff is what chapter 15 is about. And the last thing we're going to talk about in chapter 15 is what happens when you add or remove a substance. So we are at equilibrium and we have equilibrium concentrations, and then we are going to apply a stress to the system, and we want to know how the system will react. How will it change? So you're going to look at addition or removal of a substance, whether that be a reactant or a product. We're going to do changes in volume and pressure. How does that affect the reaction at equilibrium? Changes in temperature, and finally a catalyst. I like this. This is one of my the most interesting parts, really, because, like I said, it has applications in not just chemistry, but biology, wildlife management, transportation, and so this process is called Le Chatelier's principle. So Le Chatelier's principle states when a stress is applied to a system at equilibrium, the system will respond by shifting in the direction that minimizes the effect of the stress. Now, you guys know this. You know this in real life. When you get stressed out, your body shifts in such a way as to relieve that stress. Maybe it causes you to break out. Maybe you notice you're more hyper or something to combat the stress. There's this whole thing about homeostasis and equilibrium that you see in everyday life. You know, they talk about work-life balance. Works too much, it stresses you. That's a stress. And then you go back to the life part. The life's too stressful. You go back to the work part. So it kind of goes back and forth here. So in this context, stress refers to a disturbance of the system and at equilibrium. So here's what I want you to remember. Everything we're talking about in this section, we are at equilibrium, and now we're going to apply the stress. So what are the stresses? The addition of a reactant or product, the removal of a reactant or product, the change in volume, and that generally changes pressure, but that's a tricky one. That's the one the students have the most difficulty with, and then change in temperature. That one's fairly easy. Shifting refers to whether the reaction is going to go in the forward direction or the reverse direction. That's what we mean by shifting. Does it go left to right or right to left? Does the products increase or does the reactants increase? All right, so let's look at our system here. So the first thing is you got to have a balanced chemical equation. We've known this all along. You have to have the phases of matter. That's really important. You have to know that the reaction's reversible. So we see that the reaction is reversible. You know how to write the equilibrium expression or the reaction quotient expression. It's the products over the reactants raised to their respective powers. So you know how to do that. So these are non-equilibrium concentrations, and the brackets mean moles per liter. And you can convert moles, if you need a mnemonic for that for moles per liter that you've had in chemistry 170 or Gen Chem 1, you know that molarity equals moles per liter, and then you can convert from moles if you know them. You can go from grams to moles if you know the molar mass, right? Or vice versa. So molar mass is the key here, and I'll just make this fancy M to represent molar mass. All right, so we plug in the concentrations. These are initial concentrations. And I will say this, a lot of times, and they're doing it here, but they didn't do it previously, If it's not equilibrium concentrations, they use parentheses. And so that has been the convention of most books. I didn't mention it the last time, but generally we use parentheses when we convey non-equilibrium concentrations. So we calculate out QC, and it's 0.297. All right, and so that's equilibrium. So these happen to be, I guess, equilibrium concentrations up here, because they're saying that's what it is, right? So then it says we increase the nitrogen concentration. So we go from the original 2.05, we're going to increase the nitrogen concentration to 3.51. So what I want you to think of is a seesaw. If you think of a seesaw, you get about every one of these correct. So we're at equilibrium. We're balanced. If you increase the nitrogen concentration, then there's more nitrogen on the reactant side, and the seesaw is not balanced anymore. So for the seesaw to become balanced, the reaction has to go in the forward direction. Nitrogen has to be consumed, and ammonia has to be formed on this end. And so looking at this relationship, this has got to get larger, and these have got to get smaller for that reaction to happen. So this is what you have for the equilibrium, the reaction quotient. This is the reaction quotient. This is equilibrium. So what we have right here is Q is less than Kc. Q is less than the equilibrium constant at concentration. So we've talked about this previously. If Q is less than K, then you know the reaction shifts in a forward direction to increase the product and to decrease the reactants. So that's what we did. We were at equilibrium. This was the equilibrium value. So again, up here, these are equilibrium concentrations. This is the equilibrium constant right here. Then we increase the concentration of the nitrogen, and its value is less than K, and so if Q is less than K, the reaction has to shift to the right. So if Q is less than K, which we've talked about this before, this is not new to us. Q less than K, reaction has to shift to the right to get back to equilibrium. So an equilibrium that is stressed in such a way that Q becomes less than K will shift to the right to reestablish. Likewise, if we apply a stress where Q becomes greater than K, then we'll shift to the left to reestablish equilibrium. So really what we're getting at here is Q greater than K or Q less than K, or do we happen to choose Q equal to K? We've already talked about this in the previous video. Nothing's really new here. It's just that we're talking about stresses, and we're talking about Le Chatelier's principle. All right, so here it is. I want you to be able to do this problem. And I want you to be able to do it fairly quickly for like an exam or a quiz. So it says hydrogen sulfide is a contaminant commonly found in natural gas. It's that rotten egg smell. It is removed by the reaction with oxygen to produce elemental sulfur. So here we have a balanced chemical equation. You've got to have that. You've got the phases of matter. Oh, notice this is a heterogeneous equilibria. And then there's another gas there. It's not pure liquid water. It is gaseous water. So that's going to be part of the equilibrium expression. So let's draw down the players right here. K is the equilibrium constant, and it is equal to the water concentration raised to the second power divided by the hydrogen sulfide concentration. And some of you are saying, why isn't this called dihydrogen sulfide? Because it's been around a long time, and they just call it hydrogen sulfide. Notice the sulfur is not in the expression. It's integrated into the rate constant because this concentration is not going to change appreciably through the course of the reaction. As long as there's some sulfur present, its concentration remains pretty much constant. Now, so we're at equilibrium, everything's at equilibrium, and now what we're going to do, we're going to start applying these stresses. So when we apply this stress, the addition of oxygen, I want you to think of that as the seesaw again. We were at balance. We were balanced on the seesaw. When we apply oxygen, it's unbalanced. There's more oxygen here than should be. And so that means this concentration has gone up. The overall ratio has gone down. And again, when we're not at equilibrium, we use Q. And so in this case, Q is less than K. So really let this sink in again. So let's talk about it one more time, because this is what's really important. This is the most important slide here. We are at equilibrium, and we have a value for K, the equilibrium constant. You add oxygen, which causes an imbalance. Now there's more mass on the reactant side than the product side. And oxygen is in the equilibrium expression here. So this increased the concentration of the oxygen, which made this overall value less, because if you increase the value in the size of the denominator, the overall value is going to be less. So once we change the oxygen, we're no longer at equilibrium. We are at reaction quotient. We are at reaction quotient expression, and it becomes less than K. So knowing that this new set of values here, especially the oxygen, and Q is less than K, you know the reaction is going to shift to the right to relieve the stress. Now, you see it here as well. On the seesaw, to get this back to level, some mass is going to have to change to the other side to get back to level and to equilibrium. All right, let's look at the next one. The removal of hydrogen sulfide. So here's hydrogen sulfide. It's on the reactant side. We were at equilibrium, and now we're going to remove the hydrogen sulfide. So we removed hydrogen sulfide. That makes the reactant side less than what it should be. So if we remove hydrogen sulfide, all right, now this is fixed. We're not changing the oxygen. We remove hydrogen sulfide. This number is less than what it should be, and the overall ratio is greater. So in this case, for this B, Q is going to be greater than K. So once you change the hydrogen sulfide, you're no longer at equilibrium. You're at the reaction quotient. You remove the hydrogen sulfide, and so the hydrogen sulfide concentration decreases. That's why I got the arrow pointing down. And overall, this gets smaller, which makes the overall ratio get larger, and that's why Q is greater than K. So Q greater than K, the reaction has to shift to the left. Some of the mass on the product side has to get back over to the reactant side to get back to balance. So that's what's going on with B. All right, the removal of water. Well, water's a player. Here it is, the removal of water. It's in the expression. So if I remove water, that's going to make this reaction like this, right? It's gotten lighter on this side because we removed water. So the ratio here, that's what I want you to really think about is ratio. The overall expression here, this ratio, when I remove water and the hydrogen sulfide and oxygen were fixed, if I remove water, the water concentration decreases, and we're going to get into the Q is less than K again for this one. And so we know the reaction is going to have to shift to the right to make up for that loss of water. So removed water, that's going to produce more sulfur and water. Because if we remove water, the reaction has to shift to the right. More sulfur and water is going to be produced, and hydrogen sulfide and oxygen are going to be consumed. All right, what happens when we add sulfur? So we're at equilibrium, and we're going to add some more sulfur. Well, here's where it gets tricky. There's already sulfur present. If I add some more sulfur, it's not going to change the concentration. Let's think about it here. You've got this pile of sulfur, and the molarity is, let's say it's 25 moles per liter. Whatever. If I add more sulfur, here's a bigger pile of sulfur, well, the concentration is still 25 moles per liter. Because we increase the volume, we increase the number of moles, so the addition of sulfur has no effect on the equilibrium. The addition of sulfur has no effect. on the equilibrium. Q is equal to K, if you want to think of it that way. Q is equal to K. Oops. Q is equal to K. There's no change. No change. No shift. Neither. All right? That is the summary of Le Chatelier's principle right there as far as dealing with concentration. And you need to be able to do that. So again, what do? They write the expression. Notice they don't use K, they use QC because we're going to be changing one of these concentrations. And then they talk about the scenarios, which we've already done. Shift to the right, shift to the left, shift to the right if you remove H2O, and no change for the last one. These are easy. I think these are easy once you understand it. This is much easier than doing some big calculation with logarithms, right? That we had in kinetics. All right, so let's look at a visualization here. So here we have dinitrogen tetroxide, and then we have nitrogen dioxide. Both of these are gases. This is a balanced chemical equation. This is reversible. Now we have a visual down here. Here's nitrogen dioxide, and for some reason this one's harder to see, but there's a nitrogen there, and there's a nitrogen there, and there's an oxygen, 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 and oxygen. All right, so what we're going to look at here is changes in volume and pressure. So this plunger represents pressure. That's the way we visualize it. If I move the plunger down to here, by decreasing the volume, and all these particles are now trapped down here, which way do you think the reaction shifts? All right, so if this is the equilibrium concentrations, and I move the plunger from here down to here, so I've decreased the volume change is negative. What do you think happens to this reaction that was at equilibrium? Which side is going to be affected the most? Well, it's going to be this side, because look at the equilibrium expression. It's Kc equals the concentration of the nitrogen dioxide squared divided by the dinitrogen tetroxide. So because this term is squared, a decrease in volume is going to affect this side more so, because what is this really? This is moles divided by volume, liters. This is moles divided by volume, which is liters. So if the volume decreases, the same for both of these, this one's affected more because it's squared, right? And they're both gases. So that's going to cause this to go like that. The seesaw is going to be bent down like this, because as this volume decreases, this concentration is going to be squared, and that's going to be larger than what we have going on down here that's not squared. So the reaction is going to have to shift to the left to get back to equilibrium. All right, so let's look at that. I think they're going to do it better. I'm just talking about it, conceptually here, and then we'll look at it. So here it is, QC. Here's our reaction. It's nitrogen dioxide over dinitrogen tetroxide. And we put in, and we've decreased the volume. And so they've decreased the volume, and now you can see this is affected more than this. So what they want you to do is compare that to what we had before. Let's go back. Okay, this was 0.643 molar, and this was 0.0547 molar. And what's happened is we're decreasing the volume. So if we decrease the volume by half, it's going to double the concentration. That's what you're seeing here. Then we're squaring this term, and then we find out that 9.31 times 10 to the negative third is greater than the equilibrium constant. It's greater than the equilibrium constant. So the reaction is going to have to shift to the left to get back to the equilibrium constant. So what we calculate here, this is actually QC. And if Q is greater than K, if Q is greater than K, whatever. Q greater than K, the reaction shifts to the left. We already know this part. If Q is greater than K, the reaction shifts to the left. And we did that by, when we decreased the volume by half, that made these concentrations double. But this one's squared, and that's what really affects it, right? So that's what we're doing here. So I like to look at it this way. It was 1 mole of gas on one side, and it's 2 moles of gas on the other side. And if I apply pressure, or by decreasing the volume, if I decrease the volume, this side will want to shrink down to 1 mole to decrease that stress. And that's what's happening here. So Q is greater than K because this part changes more than this part, which makes it greater than K, and the reaction has to shift to the left to get back to K. So in general, a decrease in volume of a reaction vessel will cause a shift in the equilibrium in the direction that minimizes the total number of moles of gas. That's what you want to think. Shifts the equilibrium in a direction that minimizes the total number of moles of gas. Conversely, an increase in volume will cause a shift in the direction that maximizes the number of moles of gas. That's the bottom line. That's what you're learning right there, and then you're going to apply it. All right, so what I want you to do is I want you to read this, stop the video, work these out on your own, and see if you're getting this right or wrong. All right, so stop the video. All right, welcome back. So the first thing you're going to do is you're going to write the expressions for each one of these reactions. This is homogeneous. All these are going to be in the expression. This one's heterogeneous. These solids are not going to be in the expression. They're going to be integrated into the rate. They're in the expression. They're just integrated into the equilibrium constant. And then this last one is all going to be in the expression. So the first thing you want to do is write the expressions, because that'll tell you who the players are. So let's look at that. So, yeah, I think I would have done. Let's go on. Let's see if they would have showed that. Well, they didn't actually do it that way. So let's go back. I would have, at this point, just real quickly, I would have just said Kc is equal to the concentration. Well, let's do it this way. Yeah, I mean, we can call it QC. QC is equal to the phosphorus trichloride times the chlorine. That's my products divided by the phosphorus pentachloride. So I can see who the players are. This is homogeneous. They're all gases. For the second one there, I've got QC equals the sulfur dioxide raised to the second power divided by the oxygen raised to the third. Notice the lead 2 sulfide and the lead 2 oxide, they're constant. They're solid. So they're integrated into the reaction quotient already. And then this one down here, you have hydrogen iodide, and that's raised to the second power, and you're multiplying that times the hydrogen concentration times the iodine concentration. All right, so the other thing that you need to be aware of is you're going from 1 mole of gas to 2 moles this way, 1 mole of gas to 2 moles. Here you're going from 3 moles of gas to 2 moles. And the last one, it's 2 moles to 2 moles. And that one's the one that gets the most students. Nothing happens here. If I decrease the volume, it affects everything equally, so equilibrium's not going to change for the last one. But if I decrease the volume on the first one, if I decrease the volume, this side's affected most. And what's going to happen is if I decrease the volume, this is going to get overall larger. And this is then what is going to do, this is going to do. And so that tells me that Q is going to be greater than K. If Q is greater than K, the reaction shifts to the left. all right, to get back to K. So that means these are going to have to decrease. This is going to have to increase to get Q back to K. In the second scenario, Q is going to be less than K. Let's look at it here. As the volume decreases, this is affected more than this. This is going to get larger than this. So Q is going to be less than K because as the denominator gets larger, the overall ratio gets smaller. And so Q will be less than K and the reaction will shift to the right towards the products to make up for the loss, the pressure, the volume change. All right. And then the last one, since they're both 2 moles, there's no effect here. No effect. So there you go. Shift to the left, shift to the right, and no shift for the last one. I really like Le Chatlier's principle. To me, it's easy. It seems easier than a lot of the stuff we've been doing. All right, so that's the effect of pressure on, or effect of volume changes on equilibrium. You know, so here's something you need to know right here. This is really important. A change in concentration or volume may alter the position of the equilibrium, but it does not change the value of the equilibrium constant. There's only one thing that can change the value of an equilibrium constant, and that's temperature. Why? Because remember what it is. The equilibrium constant is K forward over K reverse, right? When they talk about that, let's go back to that slide just to make sure. Maybe it's K. So let's go back. Let's go back and let's see what's going on. So let's back up. At the beginning of this chapter, which has been a long time ago. This is not the most efficient way to do this. Probably driving you crazy. Right there. See, the equilibrium constant is K forward over K reverse. So the only thing that can change the equilibrium constant is a temperature change. All right? So rate forward is equal to rate reverse when we're at equilibrium. So K forward divided by K reverse, the equilibrium constant is equal to the concentrations. So that's what's going on. And let me help you out here. We'll just go through the slide sorter this time. So that's where we are right there. Whoops, I didn't do that right. It's not letting me do this without clicking through like this, so let's go with that. That was crazy. All right, so we're looking at this, and we just said that the only thing that can change equilibrium constant, because the only thing that can change the rate constants is temperature. So we're going to look at the effect of temperature. I just want to say one thing, though, before we do this. And I don't know why they didn't show it on the previous slide. If all you're doing is you're increasing, you're changing the volume, which changes these concentrations, right? And it doesn't do any effect here because it's 2 moles on this side and 2 moles on this side. But if all you're doing is increasing the pressure of the container with, like, let's say, addition of an inert gas like nitrogen to this reaction, that has no effect on the equilibrium. So the only way these are being affected by pressure is when you decrease the volume or increase the volume. So because that actually affects the concentration, which is N over V. But if you apply a gas and increase the pressure that way, and that gas doesn't react with any of the substances, that has no effect as well. I think it's discussed in the book, but I think it's funny they didn't do a slide on it to kind of accentuate that. All right, so let's look at temperature. I think this is the one that's the most missed, and the reason why I think it's the most missed is because you have forgotten in Gen Chem 1 exothermic and endothermic reaction. So here we have heat being applied to dinitrogen dioxide, and it is forming 2 moles of nitrogen dioxide. And the standard enthalpy change is 58 kilojoules per mole. So the first thing I'm going to ask you is this an exothermic reaction or an endothermic reaction? Well, this one's endothermic because it's a positive value. Exothermic would have a negative value here. So it's endothermic. It means it takes energy. Heat has to be applied. It's a reactant here that has to be applied to convert the dinitrogen oxide into 2 moles of nitrogen dioxide. So it says increase in the temperature, adding heat will shift the reaction forward because heat appears on the reactant side. So let's show you what happens here. You're at equilibrium. Heat is on the reactant side, so you're adding heat. That means the equilibrium gets out of whack like so. And the reaction is going to have to shift to the right, forming more product to get back to equilibrium. All right. I like this. It's the same thing. All these equilibrium can be done like a triangle. You could write this as your product over the reactants, and if this increases, then Q is going to be less than K, and if Q is less than K, it's got to shift to the right to get back to equilibrium. So it's all about reaction quotient and equilibrium constant, and you can do that. You can see it. There's more than one way to solve this problem. All right, so let's look at this one. The Haber process, which is used industrially to generate ammonia, largely the production of fertilizer, is represented by this equation. Notice it's balanced. Notice the phases are present. And notice that it is reversible. Using the data from Appendix 2, calculate the delta H of the reaction. So you got to calculate this on your own. The standard enthalpy of reaction. This is what we covered. This is one of the last sections we covered in Gen Chem 1. If you don't know this, you're going to have to go back to the slides in Chapter 5 or read Chapter 5 and kind of learn this over again. All right? So I'm not going to do that here. They may show it on the next slide. But you got to use Appendix 2 and the delta H's. So here it is. This is called Hess's Law. We talked about this in Gen Chem 1. It is a summation of the number of moles of standard enthalpies of formation, which you look in a table in the back of the book, minus the summation number of moles of standard enthalpy of formation of reactants, which you look in the table in the back of the book. So this is what it looks like when we break it out. And then we look these up in the back of the book, and there they are. We plug those in. Now, any pure element has a delta H of 0 by standard enthalpy of formation of 0. And the standard enthalpy of formation of hydrogen is 0 because that's its elemental form. This is nitrogen's elemental form. And so when we calculate the delta H for this reaction that we were looking on the other page, we find out that it's negative 92.6 kilojoules per mole. So the standard enthalpy of this reaction is negative 92.6. And my question to you is this exothermic or endothermic? Well, because there's a negative sign present right here, it's exothermic. And they tell you that. This reaction's exothermic. So it says the equilibrium will shift to the left if the temperature is increased. So what this means is you've got reactants going to products plus the release of heat. So that heat is a product in this reaction. So we're at equilibrium. You're going to add, it says if the temperatures increase, that's more heat on this side. And that's going to cause this to go out of balance like so. And the reaction's going to have to shift to the left to get back to balance. So you can do it by the seesaw method, or you can work it out mathematically, but It really comes down to if it's exothermic, the heat's on the reactant side. If it's endothermic, like we saw in the previous reaction, the heat is on the reactant side. So let's look at that again. So here you had heat on the reactant side. So if you add heat to this reaction, it comes down here, and the reaction is going to have to shift to the right to decrease that heat. But this other reaction, so this is an endothermic reaction. The one we just looked at, though, was an exothermic reaction. We calculated that it was exothermic. And how do we know? Because it's a negative value right there. And so if we increase the heat, it's going to form, it's going to go in reverse. It's going to go to the left. If we lose heat, if we lose heat, then the reaction will shift to the right. That's what it says right here. If we lose heat, so the temperature, so to the right, if the temperature is decreased. All right, that's it for temperature. Let's go on to the last step, and that is catalyst. So a catalyst speeds up the reaction by lowering the activation energy. That's what we learned in the last chapter on kinetics. All right? A catalyst lowers the activation energy, but it lowers the forward reaction and the reverse reaction to the same extent. So a catalyst does not alter the equilibrium constant and does not shift the position of the equilibrium system. So catalyst has no effect. All that happens is the reaction happens faster, but it doesn't affect equilibrium. So let me just show you what I'm talking about here. So here you got reaction. Here you've got energy. Here is my reactant. Here is my product. And we have to overcome the activation energy before we go down here and become product, right? So this is what my curve looks like. So in this case, the activation energy is from here, the reactant, up to the top of the peak. So if I lower the activation energy, all it does is it affects both equally. I don't have to go up as far this way, but from product to reactant, I've also lowered the possibility of how much energy is required. So it affects a catalyst. Yes, it lowers the activation energy, but it affects the forward progress and the reverse reaction equally. So a catalyst has no effect on the equilibrium of the system. Yes, it happens faster. We get the equilibrium faster, but it has no effect on where the equilibrium is going to lie. All right, that does it for Chapter 15. I hope you found this helpful. I think this is a very important section. Le Chatelier's principle is super important, but I think it's easy too. So if you're not behind, I think it's easy to learn this and do well. It's all about, to me, when I'm doing these problems, you can do it mathematically, but the quick way is just draw a seesaw and think about how the addition of one thing is going to cause a shift the other direction to relieve that. So shifting to the right here. So if I add more here, that means Q is going to be less than K. And you go, how do you know that? Because if this is the reactant and this is the product, and I'm adding more reactant, then this thing gets out of balance like so. And we know that Q for this is equal to product over reactant. And so if we increase the reactant, then the overall ratio gets less than K. And so we get the seesaw looking like this, and the reaction has to shift to the right to make up for that extra reactant that we added. So you got to spend some time with this. It's something that, maybe you don't get the first time. You got to do some problems. I tell you to do the problems in the back of the book, the odd problems, and I think that'll be helpful. But that's it for Chapter 15. And now we're going to use these tools, all the tools we talked about in 15, and apply it to the new ideas about pH and pOH and acidity constants and basicity constants. So that's where we're going with this. All right. Questions? If you do, email me.